press the bell icon on the YouTube app and never miss another update.
In the previous class, we have discussed about introduction of waves, definition of wave and wave motion, mainly the types of waves, right? That is one type of classification depending upon the number of directions in which the waves propagate, one-dimensional, two-dimensional and three-dimensional wave. And second classification based on whether a wave requires a material medium for their propagation or not, right? They are mechanical waves like sound waves and electromagnetic waves like light waves. So when say air is propagating through air, the air particle, right, executes simple harmonic motion producing disturbance, and sound propagates through air carrying both energy and momentum. Suppose if sound is produced in water, water molecules begin to vibrate, right, and transfer the disturbance. Suppose if sound is produced in any solid, the solid particles vibrate, right, propagating sound waves. That means in all gas, liquid and solid, right, sound wave can propagate, but while propagating sound wave, the particles of the medium vibrate, right. For example, when we take water in a tank, right, glass tank, you put the vibrating tuning fork at one end, and we see, when we insert the hand, we see the vibration in water. But electromagnetic wave does not require any material medium for its propagation. However, it can propagate through, right, material medium. For example, light, right? Light requires no material medium, but it is also moving through, right, material medium. So say when a torch is switched on and light rays are made to pass through the water in the glass tank, when you insert the finger in it, we don't find any vibration. Then what is it that vibrates in water? That is electric field and magnetic field in mutually perpendicular direction. One is along y direction, another is along z direction, right? And light propagates along right x direction, right? That is electromagnetic wave. Now, so it is clear whether the light is propagating through, right, this vacuum, air, water or any transparent medium, right, the vibrations are due to vibrations or oscillations of electric field and magnetic field, right. Both the fields can exist both in vacuum and material medium, right. An electric charge produces an electric field around it, right. A magnet or a current carrying conductor or a charge moving with uniform velocity, right, produce magnetic field. Both fields are vector quantities having both magnitude and direction. Now we will take up the third classification. Right, this classification, it depends upon right. So direction of vibration with respect to direction of propagation. Right. Now, based on this waves are classified into two types. That is transverse waves and longitudinal waves. So first classification is that it is transverse wave. So a wave which propagates through a medium such that the particles of propagating medium vibrate perpendicular to the direction of propagation is called as a transverse wave, right? So in transverse wave, direction of vibration of the particles of medium, that means the medium in which the wave is propagating, is perpendicular to the direction of propagation. Perpendicular to the direction of propagation. For example, we can take when we have a wave, right? A wave which is propagating along this direction. This is direction of vibration. Then the particles will vibrate perpendicular to the direction of propagation. This is direction of vibration. Such a wave is a transverse wave. Here, if you take the angle between the direction of vibration and the direction of propagation, it is always equal to 90 degrees. Remember that the angle between direction of vibration of particles and direction of vibration, right, is 90 degree. So far in this chapter, entire chapter, we are discussing mechanical waves, right, like sound waves, right. But in the next year, second year, right, we will discuss the light wave. Light waves are electromagnetic waves. Therefore, here the vibrations are only vibrations of particles of material medium. Now, number one we can take. Now, this is right waves on stretched string. Waves on stretched string, right, like veena, guitar, violin, etc. Right here, when a stretched string between 2 points vibrates, the waves produced, right, and propagate. This is the direction of propagation, and this is the direction of vibration. That theta is equal to 90 degree. Now, number two, you can take. So, water waves on surface of water. You might have seen the ocean waves, right? So in the seashores, right? You might have seen, right? Those waves on the surface, right? In a beach, right? Are right transverse waves, right? And they move like this. Again, the direction of propagation and direction of vibration are perpendicular to each other. Now, again, light waves are electromagnetic waves. Now, the third one, light or electromagnetic waves. Not only the visible light, right, gamma rays, X-rays, right, etc. are right, electromagnetic waves. When light propagates through a medium, right, now light is propagating along its direction. This is direction of propagation. Then electric field vector vibrates along y direction, and the magnetic field vector, right, vibrates in z direction. Right? So you see, this is the angle theta, and this is the angle theta. Here theta is equal to 90 degree. Electric field and magnetic field are mutually perpendicular to each other, right? That is along x, y axis and z axis. They are also perpendicular to the direction of propagation, right? That is along x axis, right? So these waves are electromagnetic waves. In fact, all electromagnetic waves starting from gamma rays to radio waves are electromagnetic waves. They consist of electric field and magnetic field. Therefore, they are all transverse waves, right? One thing has to be noted that here. So, when we apply a deformation force on a body, there may be change in length, change in shape, change in volume, right? Now, when deformation forces are removed, the body tries to regain its original configuration, original length or original shape or original, right, in volume. So in doing so, right, they generate waves, right? Maybe transverse wave or they may be, right, longitudinal wave. Now we will take a string which is stretched between 2 points, rigidly stretched. As you see, the string on instruments like guitar, veena, violin, or in when you come to the laboratory, you see a device called as a sonometer, right? Now, when it is moved, right, plucked at this point, or by keeping at the NDA, and it is moved up and down, right? Now, a transverse wave is generated on the string, right? So, when the string is moved upwards, an elevation is produced. This is called crest. When string is moved downwards, right, a depression is formed. Now it is called trough, right? So this alternate troughs and, right, crests, right, propagate through the all along the length of the string. This is crest, trough, crest, trough, crest, trough, like that. It appears like right, water waves, right? Not exactly, but it appears like water waves, right? Here it is clear what are the changes that has taken place when I applied deformation force. Deformation force when I applied, now that causes change in shape. That causes change in shape. That means no change in length or volume. There is no change in length or volume of the string. Only the shape changes when the force applied, right? In order to retain it's a straight shape AB, right, the particles began to vibrate, producing disturbance, and that disturbance moves from point A to point B, carrying both energy and momentum. So it is clear in transverse wave, right, vibrations are perpendicular to the direction of propagation, right? Now a transverse wave consists of, right, a series of alternate crests and troughs when it propagates through a medium, right? Now the maximum displacement of the particles of the string in positive direction or in upward direction is called as crest. The maximum displacement of particles in negative direction or downward direction is called as trough. So what has happened when we have generated transverse waves on a stretched string? There is only a change in shape but no change in length and volume, right? Therefore, right, we can come to the conclusion. It's very important. So whenever we apply deformation force to a medium that changes only shape of the body or medium, then, right, transverse waves are generated, right? Now since here there is no change in volume, right, there is no change in pressure and density of the medium along the direction of propagation. Is that clear? So a deformation force that tends to change only shape of a medium, right, generates transverse waves. When a transverse wave is propagating through a medium, whatever it may be, right? Now, whatever it may be means generally solids, right? Now, propagating through a medium, there is no change in pressure and density because there is no change in volume, right? So only the shape changes here, right? Where can we change the shape, right, among the solids, liquids and gases, right? Now solids have definite shape. Liquids and gases do not have separate shapes, right? So therefore, right, so transverse wave can be generated only in solids among the medium, right, and right on surface of liquid. In air and inside a liquid, we cannot generate right, the transverse wave. It is because why the transverse wave can be generated on a free surface of liquid? Because every liquid maintains a free horizontal surface. It is one of the properties of liquid at rest. Therefore, any attempt to disturb the equilibrium position of the particle on the surface began to vibrate, right, about their mean position perpendicular to the direction of propagation of the wave. Keep in mind, transverse waves can only be generated in solids, right, and on surface of liquid. They cannot be generated in right, air and liquid. The reason is that, right, a medium, particles of the medium vibrate perpendicular to the direction of propagation only due to change in shape. Since liquids and gases do not have, right, definite shape, we cannot generate, right, transverse wave inside a liquid and inside a gas like air, right? Is it clear? Now, the second type of waves in this criteria are longitudinal waves. Right. The waves, when propagating through a medium, if particles of propagating medium are vibrating along the direction of propagation, or parallel to the direction of propagation, then the wave is called as a longitudinal wave, right? That means in a longitudinal wave, right, particles vibrate along the direction of propagation of wave. Right. Now, for example, we take, right, so when I represent it in a diagram, if the wave is propagating along positive x direction, this is direction of propagation, then the particles of the medium vibrate parallel to the direction of propagation or right along the direction of propagation. This is direction of, this is the direction of propagation of the wave. Such a wave is called as a longitudinal wave, right? Now, right, example 1, we can take sound waves in A or right longitudinal waves, right? Whenever a sound is produced, any vibrating body in a material medium like air produces sound, right? Now, when we are talking, the vibration of the vocal cord produces sound waves. So, in musical instruments, the vibrations of the string, right, produces sound waves, right? When we ring a bell or when we drop a vessel, sound is produced. In all the cases, right, sound is produced due to vibration of particles of the medium. Now, number 2, you may have seen the paddy field, right? So, when the air is blowing over the paddy fields, you might have seen, right, at one instant of time, certain right group, right, of that one. So they move, right, they allow expand, then they come closer. They expand, come closer, expand and come closer. And the wave, right, propagates along the surface of the speed parallel, and the paddy field, right, the paddy, right, that vibrates parallel to the direction of propagation. The same thing can be seen when right, wind blows with very high speed in areca nut plants. In areca nut plants also we can see when air is blowing, sometimes the trees come closer and sometimes they expand. So they compress and they expand. That is also a longitudinal wave. Right? Now, when we have a spring is attached to the load. When the load is attached to the spring, so when it is pulled down, right, and left, the spring began to vibrate. When the mass moves upward, spring gets compressed. Pressure increases, volume decreases. When the mass comes down, right, the spring expands, right? That means the pressure decreases and volume increases here, right? Therefore, when a longitudinal wave, right, propagates through a medium, right, there is a vibration along the direction of propagation or parallel to the direction of propagation. Now take a vibrating tuning fork in air produces longitudinal waves. Longitudinal wave. So a vibrating tuning fork held in air produces a tuning fork. Right now, let us have a tuning fork. Right, it appears like this. It has a central stem, and these two are called the prongs of the tuning fork. Right, when we held it rest, it is not vibrating. The air in front of the prongs on both sides appears to be consisting of a number of adjacent parallel layers, each layer having the same volume and pressure at each layer is same. Right? Now, when the tuning fork move towards right, like this, while vibrating, the air layer in front of it get compressed. And that produces a region of higher pressure, right, or a region of lower volume or higher density called as compression. Now, when the prong moves towards left, a vacuum is created. The compression is pushed forward. In that place, the air layer gets expanded. Now, in this region, the pressure decreases and the volume increases, and this region is called as rarefaction. This region is called as rarefaction, right? As the prong vibrates. As the prong continuously vibrates towards left hand side, right, you will see compressions, right, rarefactions, and rarefactions, right, alternate. This is compression, rarefaction, compression, rarefaction, compression, rarefaction, right? Now, these compression, alternate compressions and rarefaction move in a forward direction, right? That means here the disturbance due to vibration of air layers, right, get propagated through air, producing a longitudinal wave, right? So a longitudinal wave consists of alternate crests and troughs. So now we'll discuss some points. Note. So one is that a longitudinal wave consists of, right, alternate compressions and rarefactions. They are vibrating along the direction of propagation of the wave. Now we see here, when the tuning fork is not vibrating, they let V be the pressure and V be volume of each layer. Except the atmospheric pressure, there is no other additional pressure on this air layer. When the prong moves towards right, it exerts force on the air layer. When it exerts force on the air layer, right, so the pressure in the air layer increases. So here pressure increases. Consequently, air is a gas. When pressure increases, its volume decreases. Therefore, a compression is a region of higher pressure in the medium when a longitudinal wave propagates through the medium. Right. See here, when the prong moves towards left, right here, the vacuum is created temporarily, right? The pressure decreases here and volume, right, increases, right? So that creates a region called as rarefaction. Then what is rarefaction? So rarefaction is a region of lower pressure in a medium in which a longitudinal wave is propagating. Right? Now, as tuning fork continuously vibrates, so alternate compressions or rarefactions are producing. So a longitudinal wave consists of a series of alternate compressions and rarefactions, right? So see here, when no longitudinal wave is propagating through air, there is no change in pressure and volume of different parts of the medium. But when it is propagating through the medium, at compression, pressure increases, volume decreases. At rarefaction, pressure decreases, volume increases. Now we have density is equal to mass by volume. So as volume decreases, density increases. Here as volume increases, the density decreases, right? So when a longitudinal wave is propagating through a medium, right, at the compression part of the medium, pressure increases, volume decreases, consequently density also increases. At rarefactions, pressure decreases, volume, right, increases and density decreases, right? Now here the deformation force is applied by vibrating tuning fork on the air layer, right? So that deformation force changes volume of the air layers, right? Here the volume increases, here the volume decreases, right? So another point, longitudinal waves are generated, right, when deformation force changes its volume. This volume of different parts of the medium, right? So when does transverse wave generated? When shape of the medium changes under the action of deformation force, transverse waves are produced. When volume of different parts of a medium, right, changes due to deformation force, right, longitudinal waves are generated, right? And we know that liquids and gases do not have definite shape, but they have different volume, right? Even gases do not have different volume, that depends upon the pressure, right? Now, so in solid has both different size and different volume. So a deformation force can change volume in solids, liquids and gases. In all the cases, right, the longitudinal waves are generated, right? So it is clear that, right, transverse wave can be generated only in solids and on surface of liquids, right? But longitudinal waves can be generated in solids, liquids and gases because all of them undergo change in volume when deformation force applied tries to change the volume of these three medium, right? Is that clear? Right. So another important thing, when a transverse wave propagates through a medium, there is no change in pressure and density of different parts of the medium along the direction of propagation. When transverse wave is propagating along a stretched string, right, all particles or all parts of the string have same pressure and same density. But when a longitudinal wave propagates through a medium, right, there is a change in pressure, volume and density in the direction of propagation, right? So when a longitudinal wave is propagating through air, at compressions pressure decreases, pressure increases, volume decreases, density increases. At rarefactions, pressure decreases, volume increases and density changes. So here, right, since there is a change in pressure and volume, so we can apply gas laws here, right? Boyle's law, Charles' law, right, can be applied to study the change in pressure and volume. And of course, if the temperature remains constant, we will see that later. Then we use Boyle's law. If the temperature does not remain constant, we have to use the another law, right? Is that clear? Right. So this is all about the longitudinal waves, right? And now, the most important difference between a longitudinal wave and a transverse wave is that, so transverse wave exhibit, right, a phenomenon called polarization. Right? See here, when light is propagating through a medium, the electric field vector, that what we call the light vector, it vibrates, right, in all directions perpendicular to the direction. So y-axis, right, z-axis, negative y, negative z, etc. They can be resolved into two components, one component along y-axis and one component along z-axis. Such a line is called as polarized line. There is a symmetry of vibration. So when it is passed through a crystal, say tourmaline crystal, right? Now, after passing through this crystal, the vibrations are restricted to only one direction, that is y direction, right? Such a phenomenon is called as polarization. So transverse wave can be polarized. That means we can restrict the vibration to one confined plane or one confined direction, right? After passing through a polarizer like a tourmaline crystal. But longitudinal waves, right, do not exhibit polarization, right? Because here the direction of vibration is parallel to the direction of propagation, but here when we held this a slit, right, whether it is perpendicular or parallel, there is only one vibrations here, that we will discuss it later when it comes to the entire chapter, that is polarization, right? Now here one thing you have to be remember, one of the important differences between longitudinal waves and transverse wave is that transverse wave exhibit, right, phenomenon called polarization, right? longitudinal waves do not exhibit polarization, right? Whether to check a given wave is a transverse wave or a longitudinal wave, we often use this concept, right? If it exhibits polarization, then it is a transverse wave. When it does not exhibit polarization, then obviously it is a longitudinal wave, right? Is that clear? And here all electromagnetic waves are transverse waves, right? They may be one dimensional or three dimensional, right? But they cannot be longitudinal waves, right? Electromagnetic waves all are transverse in nature, because electric field and magnetic field vibrate perpendicular to the direction of propagation of light. But however, when we take mechanical wave, the mechanical wave, they can be transverse waves or they can be longitudinal wave, depending upon whether the deformation force changes the shape of the medium or volume of the medium. Take the case of vibrations of a stretched string, where the string particles of string vibrate perpendicular to the direction of propagation, generating transverse wave. It is a mechanical transverse wave, right? The wave generated on a string, right, or even on the surface of liquid, right, or transverse waves, mechanical transverse wave, right? But the waves generated by a tuning fork in air, right, are longitudinal waves. So mechanical waves can be transverse waves or longitudinal waves, but electromagnetic waves are always electromagnetic waves. They are not longitudinal waves, right? Right. So far we have discussed about the classification of waves, transverse waves and longitudinal waves. Right. Let us distinguish between transverse waves or and longitudinal waves. So, or we will compare. That is comparison of transverse waves and longitudinal waves. As far as board examination is concerned, there may be a question on this topic. Distinguish between transverse waves and longitudinal waves, or compare transverse waves and longitudinal wave. Usually there will be a 2 mark or 3 mark question on this, right? Now, so we'll take it. So on the left side, you have taken transverse waves. On the right side, you will take longitudinal waves. Now the first one it is, right? Now, right, in transverse waves, particles of propagating medium vibrate, right, perpendicular to direction of propagation of wave. It is a definition of transverse wave. Now here, right, in longitudinal waves, particles of propagating medium, right, vibrate along the direction of propagation, along the direction of propagation. Now the second comparison, right, we know that a transverse wave consists of a series of alternate compressions and rarefactions, right, whereas a longitudinal wave consists of a series of alternate compressions and rarefactions, right. Now it consists of a series of alternate crests and troughs, right? Remember, crest is the maximum displacement of the particle in positive direction or upward direction. Trough is the maximum displacement of the particle in a negative direction or downward direction. Now here, it consists of a series of alternate compressions and rarefactions. And third, the most important thing, it exhibits polarization. Always remember that one of the sure tests to decide whether a wave is a transverse wave or a longitudinal wave is the polarization. If the wave exhibits polarization, then it is a transverse wave. If it does not exhibit the phenomenon of polarization, it is not a transverse wave, that means a longitudinal wave, right? Number 3, it does not exhibit polarization. It does not exhibit polarization. Now, fourth one, here deformation force changes shape of medium. So when transverse wave is generated, the applied deformation force changes the shape of the medium. Here, deformation force changes volume of the medium. Volume of the medium. So we are having 4 differences here, right? See here, one regarding vibration, another regarding, right, components, compression, right, compression, rarefaction, right, etc. Right. Now that is regarding polarization and regarding deformation force, right? Here, fifth one, so it can be generated only in solids on surface of liquid. They cannot be generated in air or inside liquid. Now here longitudinal wave, it can be generated in solids, liquids and gases, because all the three media possess right volume. Now the sixth one, right. So when a transverse wave propagates through a medium, right, so there is no change in pressure and density of the medium along the direction of propagation. So remember that stretched string. When a transverse wave is generated on a stretched string, only shape changes. Right, due to the change in shape, there is no change in pressure and there is no change in volume and there is no change in density. But here, right, when a longitudinal wave propagates through a medium, right, pressure and density of different parts of the medium, right, change in the direction of propagation. Change in the direction of propagation. Now that's all about this classification. Entirely in this class we have discussed about the transverse waves and longitudinal waves. What are transverse waves and longitudinal waves? How they can be generated, how do they appear or consist of, and etc. In the next class, we are going to study some basic terms. Right? The thing is, in the previous chapter, oscillation, we have discussed about a simple harmonic motion executed by a single particle. That means a bob of a pendulum or a loaded spring, etc. But see here, in case of waves, when we take, right, there are two motions. Two motions are involved here, right? We'll take the case of mechanical waves, of course, transverse waves also. The particles of the medium vibrate or execute simple harmonic motion about their mean position. What types of motion are exhibited by the particles? It is simple harmonic motion. they do not exhibit translational motion. But the disturbance, energy or momentum or wave that propagates right from one point to another point, right? So energy and momentum have a translational motion, right? But particle executes simple harmonic motion. Again, when we compare oscillation and waves, in oscillation we have discussed about oscillation of only one particle, like displacement, angular displacement, amplitude, velocity, frequency, period, right, velocity, acceleration, etc. The same concepts can be applied to the waves, and only the difference is here. Innumerable number of particles of the medium are executing simple harmonic motion. Therefore, right, a wave has amplitude, frequency, period, wavelength, wave velocity, and most important thing what we have discussed, the phase, right? So these are all the terms, right, which we are going to, right, use it here. Now here in oscillation it is applied to a single particle. Now it is applied to a wave as a whole for a large number of particles. Okay, right? Let us conclude this part of the waves, right, at this point. So hope you will understand the two waves, right, transverse waves and longitudinal waves. And one thing I would like to tell you, in the entire topic, in the next classes, we are discussing only about the mechanical waves, not transverse wave. We will discuss transverse waves, that is light waves, their properties, their phenomena, etc. in the second PUC physics. Okay, thank you very much.